AB Calculus, Notecard 71, Disk Method for Volume. This is the 71st video lesson in the series inspired by Stacy McMullen, formerly of Dowson School District, who developed the Notecard system. What this Notecard lesson does is builds upon what we learned earlier, like if you have the area beneath a curve, like if we have this function up here that I'm drawing, f of x, and we want to find the area from A to B below this curve, and so we're finding this area here. Okay. So that's going to be a two-dimensional area, and what we're going to do is revolve this. So we're building on, we're going to revolve around a horizontal axis, and we're going to take this shape here and rotate it, revolve it around the x-axis. And so if we look at it from the side, it's going to show up down here and be a volume solid that's going to be, it's going to be circular on one side. So I'm just drawing the circle here on one end, and on the other end. So you'll have this big tire looking thing when you rotate this area around the x-axis. And what is the volume going to be? Well, what you're doing is you're taking this f of x and considering it as a radius of rotation. And I'll call f of x equals r. And so if you take this equation out here, v equals the integral from a to b of pi r squared dx. In this case, where you have f of x, I like bringing this pi out front, since this pi is a constant. Pi times the integral from a to b, limits of a to b, and in place of r, we're going to put f of x. So f of x becomes our r, and we square that, and we have dx. And also we can revolve a shape around a vertical axis, and if that shape is flush up against that vertical axis, which I'm drawing right now, let's say we have a function that looks like this, but this time, okay, we have a function that is in terms of y. So we have x equals g of y. And then we are going from our limits of integration, we'll say, well, I'm going to make it, I won't make it right against the x-axis. I'm going to say, we'll say this is c right here, and then we'll say this is d up here. And so what we're doing with our limits of integration, we're taking this shape and rotating this shape around, in this case, the y-axis. And so the other side is going to show up over here, and it's going to be some type of bullet-looking shape that we have here, okay? With this being the base down here. And what that looks like is very similar, analogous to what we did up here earlier. So we take this pi out front, and our boundaries of integration from c to d. And in this case, instead of f of x here, we're going to have g of y, and square that dx. And so the steps are, one, to draw the region, find the limits of integration, find the radius in place of r, and then integrate and evaluate. So we're going to go over a couple problems that demonstrate this. Well, the region enclosed by the x-axis, the line x equals 3, and the curve y equals square root of x is rotated about the x-axis. What is the volume of the solid generated? It says without a calculator. Okay, y equals square root of x. This is a standard parent function of pre-calculus equation. So here it is, I'm drawing this. This is going to be y equals square root of x. Okay, that's step one. We drew. Okay, step one, we drew the region, right? So two-dimensional region. Step two is we find the limits of integration. Well, we have from the x-axis, line x equals 3 in the curve. Okay, it doesn't specifically give a lower limit, but we're going up to x equals 3. And so we're taking this region here. So we draw the region, we found the limits, and we are rotating this shape about the x-axis. And so looking at it from the end, if we draw this circle here, so you're going to have a base, so it's going to be a sort of a bullet shape, and that's what it's going to look like. And let's see again, did we integrate? Okay, let's find the radius. Okay, here we have y equals square root of x, and so our radius, r, is going to be equal to square root of x. Okay, integrate and evaluate. So here we go. Our limits of integration are, I'm just going to write this up and say pi. We have a to b. Okay, here we have a is equal to 0, and b is equal to 3. Okay. And we have our I'll just say r squared dx. Okay, and that's going to be our volume. Now to specify what we have here, we have pi, and our limits of integration are from 0 to 3, and we have our r value is going to be our f of x. Well, that's going to be square root of x squared dx. And just simplifying, we're going to have pi integral from 0 to 3, and the square root of x squared is x. And now working below, I'm just going to come below here, we have pi, and the integral of x dx is going to be x squared over 2. And we're integrating from 0 to 3. And so what we're going to do is this using our fundamental theorem of calculus. It's going to be our f of b minus f of a. And write that out to our right. We're going to have pi times 3 squared over 2. That's going to be our big F of b. And minus big F of a, we have pi times 0 squared over 2. And then continue to work below, we have 3 squared is 9, so we're going to have 9 pi over 2. And this other area with the 0 here, this is going to zero out. So our answer is going to be, our volume of rotation is 9 pi over 2. I hope you see how this coincides with what we've been working on from anti-differentiation on, really. Okay, next, last problem. Find the volume of the solid generated by revolving x equals the square root of quantity 1 plus y, with y equals 3 and x equals 0 about the y-axis. I don't know about you, but I'm a lot more comfortable when I just draw a sketch of a graph when that function is in terms of solve for y. So I'm going to take this x equals square root of quantity 1 plus y, and square both sides of this equation. So we're going to x squared equals 1 plus y. And so subtracting 1 from both sides, we're going to get y is equal to x squared minus 1. Okay, now making a sketch of the graph of that here. So we have xy coordinate plane. So we're going to have x squared minus 1. Well, that's going to be the parent function of y equals x squared, but drop down a unit, so we're going to be going like this. Okay? And then like this. And really, what we're looking at is the square root of 1 plus y. We are not going to have this left half. Okay, this is going to be, so I'm going to go ahead, the square root equation. We'll do this. I'm going to erase this half right here. So there we are, right? That's what we're looking at. So this is going to be the function x equals square root of quantity 1 plus y. And then it says with y equals 3 and x equals 0 about the y-axis, okay? X equals 0. With and without a calculator, right? So we have y equals 3. And x equals 0. So what we're doing is we're taking this shape here, and we are revolving that shape about the y-axis. So again, we are three-dimensionalizing this shape. And looked at it from above, we're going to see a circle. So again, we're talking about a bullet shape. And what are going to be our limits of integration as far as finding this? Well, x equals 0, that's x equals 0. I don't see any lower limit here, so I'm thinking we're going from -1. So we're going to say that's going to be c, and d is going to be equal to 3. Okay, so we're taking this shape here, and to do that, we're going to take our volume is equal to pi, our integral from c to d, and we have -1 to 3, and we're going to have g of x, or g of y, which is square root of quantity 1 plus y squared dy. Okay, now, working to the right, we're going to have pi, we're going to have the integral from -1 to 3 of 1 plus y dy. All right, working below equals pi. We're going to have the integral of 1 dy is going to be y, and then we're going to have plus the integral of y dy is y squared over 2. And we're going to evaluate between -1 and 3. Now just plugging in here, we're going to have pi, and by the way, it's going to be pi times both of these things here. So we're going to have 3 pi. You see that? That's 3 times pi plus Again, we're going to have pi there as well, plus pi times 3 squared over 2, and that's going to be our big F of B. Well, it's C to D in the way they have it set up here, right? C to D, but it's like big F of B conceptually, minus, we're going to have, plugging in -1, we're going to have -1 times pi plus pi times -1 squared over 2. Okay, and now just kind of working below, we're going to have 3 pi plus 9/2 pi, and we're going to subtract out, well, minus minus, so we're going to have, this is going to be plus pi, and then we're going to have over here minus, because this -1 squares out, so we're going to be minus pi over 2. So that's going to be 3 pi is going to be 6 pi over 2 plus 9 pi over 2, and then we're going to have this plus pi is going to be plus 2 pi over 2, and we're going to be minus pi over 2. So that's going to be 6 plus 9 is 15, plus 2 is 17, minus is 16. So we're going to have minus 16 pi over 2, which simplifies to 8 pi. So 8 pi is our volume of rotation. So that's it. I hope this has been helpful to you. Again, we're just extending what we've done in the past. And the next thing we're going to go on to is, soon anyway, the washer method. Anyway, good luck, and thanks for viewing.